Welcome back to ECE 442-542. In this video, this will wrap up our Unit 4 on discrete equivalence. We're doing now the pole zero mapping strategy for finding discrete equivalence. And again, we're doing the scenario number 1, which is where we're looking at a direct input-output equivalence between h of s and h of z. We're now back into the transfer function setting, and we want to now determine how do we find a discrete equivalent, an h of z, given a analog version of that h of s. And this will now involve not only mapping the finite poles and the finite zeros, but now we will have to better understand this concept of zeros at infinity and how those are handled. And in MATLAB, they are handled differently maybe than what we will default them to be here. But all of that depends on how much time it takes for you to perform a computation if you're now doing this number crunching in your discrete system. If it takes you a long time to compute what you're trying to compute to get the output from the input, if the input is not really available at the present time, then you may want to introduce a pole zero excess in your discrete time representation that differs from how many z plus 1 factors you have included in your discrete equivalent. And hopefully we'll be able to make that a little bit more clear as we go through this discussion. The idea now of this pole zero mapping is to map the poles, and these are the finite poles of h of s to the poles of h of z, map the zeros of h of s, and this now means two sets of zeros, the finite zeros and the infinite zeros, and how many infinite zeros you map will depend on how you want to handle this number of factors z plus 1 in your discrete equivalent, and really how much computation time lag there might be in your implementation of this discrete equivalent. So you map the zeros, both finite and infinite, so maybe I should say that. And you may have a constant or some gain in the h of s expression. You'll want to now match that in the h of z expression. One nice feature of this pole zero mapping is if you start out with poles that are stable in capital H of s, because of z equal to e to the st, that mapping, that preserves or pushes everything that has a negative real part of s inside the unit circle. So if you start with a stable h of s, or all of the poles of h of s in the left half plane, those will map inside the unit circle in the h of z expression, doing this pole zero mapping or matching strategy. So the approach to do this is first to factor h of s, the analog transfer function, into pole and zero factors. That will then allow us to treat those individually so that we can now map the poles of h of s to z-plane poles using this relationship that we've already derived that relates s with z. So let's look at an example. Suppose now we had a single pole factor in this expression. The expression is 1 over s plus a. We have one pole, and where is that pole? In this particular case, we have a pole at the value of s that causes that denominator to vanish, we can set s plus a equal to 0, solve that for s, and we find that our pole is in fact at minus a. So here is our pole factor in the analog transfer function. That gives rise to this pole at s equal to minus a. So if s is equal to minus a, and we map that into a z value using z is equal to e to the st, then we have z is equal to e to the minus at. We want to now have a factor in the denominator of our h of z expression that has a denominator factor that vanishes when z is equal to e to the minus at. Or we now solve that, or set that, how do I want to say this? We now just subtract e to the minus at from both sides, and that would give us a factor that vanishes when z is equal to e to the minus at. Well, to be consistent with this pole factor, that factor really needs to be in the denominator, or now we have this 1 over s plus a expression translates into this factor of z minus e to the minus at quantity inverted. What happens if we add complex roots? Now we have s, let's look at it in rectangular form. S has a real part of minus a and imaginary parts that are conjugates at plus and minus jb. Again, using this equivalence between s and z for our mapping, we now have z is equal to e to the st. We replace s with minus a plus jb, pull that apart or separate it into two factors by knowing what we know rule-wise can be done for matrix or for exponentials. We now have e to the minus a little a capital T times e to the j little b capital T. The first piece you can see is now our magnitude of z, because e to the j whatever, in this case it's e to the j bt, if we call bt an angle theta, e to the j theta has a magnitude of 1. So the magnitude of z is r, and it has an angle of theta. Or z is equal to r e to the j theta, and if we apply Euler to that, we now have r cosine theta plus j sine theta. Again, theta is equal to little b capital T. This now we can write as r cosine theta plus j r sine theta. Or we can now say, oh, here is the real part of z. We could say there's the real part of z, and the imaginary part is r, capital R, sine of theta. Which means that if we now had complex roots in the s domain, we could associate that with a factor that's equal to z minus z sub r squared plus the imaginary component squared. We now have a quadratic factor. It has real coefficients. The real part is z sub r, and the imaginary part is z sub I. And that would then allow us, if somebody gave you complex roots in your transfer function, either zero roots or pole roots, you could now say, oh, I know what A is and I know what B is. I can find capital R and theta from the little a and the little b. I now know what capital R and theta are. I can convert that into rectangular form and write that factor. Whether that corresponded to pole factors or zero factors doesn't matter. If it's a pole factor, that quadratic expression would be placed in the denominator. Now what we want to do is map the finite zeros using the exact same mapping strategies. of capital H of S to the z-plane zeros using z is equal to e to the st. Suppose we had a numerator that was k times s plus b, and we want to now map that into a zero factor in the discrete time setting. The k may be different, so let's now just call that a k bar. But what's going to give us the appropriate z factor in the z-plane? It's now going to be z equal to e to the minus bt, or the factor now is z minus that quantity, which is e to the minus bt, consistent with how we had it up here. Z is equal to e to the st, where now s is the minus b. For our 0, we have a 0 at s equal minus b. And that now says, oh, that provides us with a factor in the numerator of z minus e to the minus bt. We now have mapped our finite poles, real or complex, our finite zeros, again real or complex, into the appropriate factors in the z domain. Now what do we do with infinite zeros? Infinite zeros, first we have to remind ourselves what those correspond to. That's really the difference between the number of poles you have, finite poles, with the number of finite zeros, or the number of poles minus the finite zeros. How many, in this example, how many finite zeros do we have? In this particular case, we actually have 2, and they are, one is at minus b and the other is at minus f. If that's the case, how many infinite zeros do we have? Well, now we need to compare the number of finite zeros with the number of poles in our denominator. If we look at the number of pole factors, we're assuming that these are all real. We have 1, 2, 3, 4, 5 factors, so that now the number of infinite zeros is 5 minus 2, or it's now 3. We now have 3 infinite zeros, and we want to now incorporate or represent those zeros at infinity by the appropriate number of z plus 1 factors in the numerator of our discrete equivalent. That means then that if we now have 3 zeros at infinity, we actually want to put in our numerator expression this factor z plus 1 raised to the 3rd power. MATLAB actually is going to reduce that by 1. So if you did the mapping or the matching strategy for the C to D using in MATLAB, you will find that if you had 3 infinite zeros, MATLAB, in fact, would give you a 2 there. It preserves at least 1 pole 0 excess in the discrete time transfer function. It doesn't now have the sum of the finite zeros and the infinite zeros in your transfer function capital H of z equal to the number of poles in H of z. For us, unless I tell you differently, you would have then this z plus 1, the number of factors, equal to the number of infinite zeros. Now if I say, oh, I want you to have a certain number of, or a pole 0 excess of some amount in the z domain, then you would maybe have to modify what this power is relative to the number of infinite zeros in your original H of S expression. The pole 0 excess is just the number of poles minus the number of zeros. Let's now look at this frequency response in the z domain relative to what hopefully you have a little bit of a feel for in the S-plane. If we're finding the frequency response in the S-plane, we're really simply walking up the imaginary axis. We start at DC and we just keep stepping up depending on the resolution, but we now simply look at particular frequencies on that imaginary axis, or we are looking at h of s evaluated at s equal to j omega. What does that do in the frequency domain? Or really, I'm trying to show you or help illustrate why this high frequency of factor z plus 1, why is that used to represent these zeros at infinity? DC is going to be consistent in the z-plane with z equal to 1. Why is that? Well, here's our frequency response in the z domain. Z is equal to e to the st, which we're replacing s with j omega. Again, we're walking up the imaginary axis in the s-plane, or now we're replacing z everywhere with e to the j omega t. Well, we know that the sample frequency is related to the sample period by omega sub s is 2 pi over capital T. What's the highest frequency that we can actually sample? And now I'm suggesting by this labeling of the z-plane that our highest frequency that we can actually represent in the discrete time setting is pi over 2. And why is that? Well, the highest frequency is now omega sub s over 2. That's the Nyquist frequency. But what is omega sub s? Well, omega sub s is 2 pi over capital T. So if we say 2 pi over capital T, but the highest frequency is half of that, we now see that the highest frequency in a sampled system is now pi over capital T. That's the highest frequency omega sub s, omega sub h. What's z at that frequency? Well, now z is equal to e to the st when s is equal to j omega high, or this is now e to the j omega sub h t, but now we have an expression for omega sub h in terms of t. That's e to the j pi over t, that's what this is, times t. But the t's cancel and we're left with e to the j pi. And what is that? Well, that's cosine of pi plus j sine of pi. Sine of pi, 0. Cosine of pi is minus 1. This is now minus 1. Or ej at some angle pi, well, pi is that angle. And if you now go all the way over there, that now represents to the location in the z-plane of minus 1. So that's why we can now say, oh, if you want to go to the highest frequency, which in the analog setting are zeros at infinity, now that's equivalent to, in this pole zero matching strategy, zeros at the location z equal to minus 1. Well, if I now have z equal to minus 1, that gives rise to a factor of z plus 1 in the numerator. And depending on how many zeros at infinity we have, that influences how the power, or how many of those z plus 1 factors we include in the numerator. So the 0 factor associated with z equal to minus 1 is this z plus 1. And again, if you need to remind yourself of what that is, well, z is equal to minus 1. We can view that many different ways. We could say, oh, that's minus 1. Well, that's a magnitude of 1 at an angle of e to the j pi. Since minus 1 is actually 1 at an angle of 180 degrees, in radians that's pi, or this is now cosine of pi plus j sine of pi, and again, that ends up being minus 1. So once we've now mapped the zeros at infinity into the appropriate number of z plus 1 factors, now we simply need to adjust the gain of h of z to match. And what do we mean by match? Well, that usually is influenced by what capital H of s is in terms of structure. For example, suppose capital H of s was low pass. Where do you think we would want to match gains between h of s and h of z? Typically, we wanted to match those in the pass band at low frequencies, and a straightforward low frequency is the extreme, DC. So we now match h of s evaluated at s equal to 0. We set that equal to h of z when z is equal to, well, this is now e to the st, and s is 0, so now we're saying, oh, e to the 0, we set that equal to z equal to 1. So this would now give us, we evaluate h of s when s is equal to 0. H of z has some unknown gain, k bar, in it. You can now solve for that k bar if you know your h of s is low pass in structure. What about if h of s was high pass? Now we might want to match gains at the high frequency, so we now might want s to approach infinity. And what value of z does that correspond to? Where are we now considering the highest frequency in our h of z? Well, that now, hopefully I've sort of rationalized why that could be z equal to minus 1. Finally, if you had a bandpass filter, you might now find whatever frequency that is. That's now omega equal to something. That's s equal to something. You now use the relationship z is equal to e to the st and match the appropriate value of z with that h of s value at the frequency in the pass band of your bandpass filter. And that hopefully now provides you with a strategy of 5 steps to do a pole zero matching or a pole zero mapping to go from an h of s into an h of z.